Good morning, everyone. Thanks for coming here so early. So some of you are going to the hackathon in Groningen I just saw, and you're going to build all sorts of cool stuff, and some of you might be doing that on top of Bitcoin. And so I'd like to show some things that people have tried in the past when they tried to do other things on top of Bitcoin that weren't specifically necessarily money, and there's some really bad ways to do that and some potentially better ways to do that. And I think it's important to keep in mind that Bitcoin is a very focused thing. It's really, I put two words on the slides, it's trying to be unstoppable money. And as soon as you do anything that is even slightly contradicting to that goal, it's going to be more difficult. Doesn't mean it's impossible, but it's just a little bit more tricky. One of the things that Bitcoin is really trying to constrain is the resources of all the computers in the network. So everybody's downloading the blockchain, and everybody is verifying the blockchain, or at least that's how you should be using it. Otherwise, you don't really know if you have Bitcoin. And when it comes to downloading the blockchain, what you generally can do is you look at every block, and then you say, okay, it's valid, and then you can kind of toss it again. So it's not, disk space not necessarily the biggest constraint there. It's ideal if you can store the whole thing, but it's not at the end of the world if you don't. But what you do need to keep track of is who owns which coins at any given time. So if you receive Bitcoin, that's basically called a UTXO, an unspent transaction output. And there's about, I think, a couple million of these unspent outputs. And that means, so that's basically a database of who owns what coins. And every time a block comes in, you look at the database and you see a transaction and you ask, does this coin that this person is spending, does that coin actually exist or not? And if it exists, then it's fine. And if it doesn't exist, well, then that has to be invalid. And so that's a lot of reading and writing. And so you want to keep that list of who owns what in your memory, in your RAM. And so if there's a huge number of individual coins, then that starts to fill up your RAM. And that's a constraint that is going to be important later on this talk. Oh yeah, I'm simultaneously switching the slides on my laptop and on this thing, so sometimes it goes wrong. So there's a really cool article, you'll find the links in my show notes later, from 2014, where people were putting all sorts of art on the blockchain. And back then, that was still doable. But the one way they did that is to create fake addresses. So if you can see on the slide, there's an address starts with a 1, and it's really just a destination of where these coins are going, but it's actually fake. So there's no way to spend that money. But if you take the characters in that address and you convert them in a special way, then you get a picture of Nelson Mandela, or you get his whole speech. And I think some people even put entire audio files on the Bitcoin blockchain. If you do that today, with fees being very low, you can do it for as little as, I think it's 40 cents per kilobytes or something. But please don't do that. But you can. The problem with this is that as far as Bitcoin is concerned, it doesn't know about Nelson Mandela, it doesn't know about art. All it sees is that somebody owns some coin that might be spent at any possible moment. So every node on the Bitcoin network is looking at these addresses in a way and is just waiting for someone to spend it. So it's just wasting people's RAM. Okay, so that's a problem. Sorry. How do we solve that? Okay, so there was a new code introduced called op_return, and what that basically does is it tells the Bitcoin node whatever is spent to this place cannot be spent ever, so don't worry about it. It's just data, and that's nice. And then after this op_return, you can put whatever you want. You can put up to 80 bytes of whatever you want, and it'll be ignored. So you don't have this problem of keeping all this data around. How is this used? Here's our friend Rare Pepe. It's a little small, but what you see on the left is a trading card, essentially, and on the right you see a sort of website where you can buy and sell these things. And the way the buying and selling goes is every time something moves, you make a transaction on the Bitcoin blockchain, and you add this little data inside the op return field that I just talked about. And then you have a special piece of software that just runs through every single Bitcoin transaction in history and looks at these op return information and says, do I understand this? And if so, okay, this is a trade. This is now moved to this other person. So you're kind of relying on external software to interpret what's on the chain, but there's still data on the chain. And at the bottom, there is a transaction. It looks like gibberish, as you can see, but the special software can read it. Okay, problem is the fees started to go up because more and more people started to use Bitcoin, and the block size at the time was constrained to 1 megabyte. Currently, it's more like between 2 and 4, depending on what type of transaction you put on it, thanks to SegWit. But fees started to go up, and so now if you try to sell one of these little trading cards, you might be paying, $20 or more of transaction cost. And that problem was made even worse because the software that was doing the trading wasn't built for a high fee market, so it was doing very inefficient things in general. It was like miscalculating the fees a lot too, so it was spending more than it had to. And so you saw a trend where other blockchains said, come to us. Bitcoin Cash did that, but other chains too say, come to us, we have low fees. And so from Bitcoin's point of view, that whole idea of putting data on Bitcoin was kind of dead, I think. But winter is coming, because this news article came out a few weeks ago, and it was claiming, and I have not checked this, that 20% of all Bitcoin transactions was used by this mysterious new thing, and it was using this op return. So that's a lot. So what was going on there, and do not worry about what this chart means, there's another coin, or another blockchain, and the way you would mine that blockchain was to publish things on the Bitcoin blockchain. So you would publish a transaction on the Bitcoin blockchain that points back to this other blockchain, and then you would publish something on the other blockchain pointing back to the Bitcoin blockchain. And then somehow, magically, you win tokens. And these tokens have some monetary value. So now there is a monetary incentive to put as much stuff as possible on the Bitcoin blockchain pointing back to this other blockchain. That's going to lead to some interesting dynamics. The fees, at some point the Bitcoin fees will be so high that this is simply not worth doing anymore. But I don't know if that's annoying for Bitcoin. I could imagine if that system is worth 100 times more than Bitcoin, then nobody can use Bitcoin anymore. But I don't think it'll go that far. But that's interesting. So my guess is that the discussions that people had in 2014, especially around how to deal with this, they're going to come back. Before I go to the next slide, there's an interesting question. I'm going to skip that question. So what I think is important to do is keep things as much as possible away from the Bitcoin blockchain, because that is a very scarce space, and it doesn't really like having things on it that aren't money. And there's a new protocol that was presented last year in Lisbon called RGB. It was presented by Giacomo Zucco and Alekos Filini. And there's really two things that are key to this protocol, and I'll be trying to explain it a little bit, but you can read about it too, of course. One is called client-side validation. What it means is that instead of trying to interpret all the rules of a smart contract on the blockchain itself, you have a separate piece of software that does most of the rule checking, and the only thing you're putting on the blockchain is some hash, some commitment to every intermediate piece of state. So you do as much as possible away from the chain. And the second thing, and that's, I think, a really cool element there, is called pay-to-contract, or alternatively sign-to-contract. And I'll try to explain that a bit more later. But the idea there is that rather than putting something explicitly on the chain, like we saw with op return, you're actually tweaking either your signature or you're tweaking the address that you're spending to in a way that for the outside world is indistinguishable from any normal Bitcoin transaction. So as far as other people are concerned, person A is paying person B is paying person C, and nothing interesting is going on. But if you know what to look for, you will recognize the information you need right inside the signature. So that's pretty cool, I think. And I'm going to explain this with an Ethereum giveaway. Yes, I am giving away Ether. How does that work? I created an asset on this RGB system that is a stable coin with 100 Finny, and that's fully backed by me. If you want to know how much 100 Finny is, Google it. Of that, I'm giving away a private key, as you can see here. You don't have to write it down. I'll give you guys a link to GitHub where you can find it. And that private key holds the rights to 10 Finny. Again, I'm not going to spoil how much that is. And there's a bunch of instructions on my GitHub, which will be there as soon as I sit down and push it there. And that'll, so what you'll be doing is you're gonna try and get these 10 Finnies and send them to me, and then I'll send you the actual Finnies. So you can do that during the workshop that I'm hosting, but you can also ask me other questions during the workshop this afternoon. Okay, so what does RGB do? So the client-side validation part, so part one, is that you are doing most of the work away from the chain. This image, again, is complicated. I don't actually like it, because I don't think it's very clear. But it illustrates, again, there's a bunch of steps happening off the chain, and there's a bunch of things happening on the chain. And one thing that's important to notice is that it's not necessarily the case that every transaction on-chain is linked. It could be that there's two different transactions that don't look linked as far as the chain is concerned, but they are linked as far as the protocol is concerned. So you can get a pretty good privacy that way. Because otherwise, even let's say you have a protocol where even though the information you're putting on the chain looks like gibberish, there's all these companies out there that do chain analysis and that try to figure out what you're trying to do. And they might still be able to figure out, oh, well, this is probably these guys doing this specific protocol. So you want to blend in. Okay, so what does it actually do? So there's a contract which you define in software, and this contract has a bunch of fields. So it has a title. In my case, this 100 Finny title has an amount. And the most important part there is that this contract itself is pointing to an initial coin or unspent output on the blockchain. So it is pointing to a specific transaction, essentially. And that way, when the software is checking the blockchain, it sees this contract and it knows what transaction on the blockchain to look for to start. So in this case, it's a very simple contract. It just creates 100 tokens and it can move those around, but the contracts can be very complicated. And then what you do is you hash this contract and then you put the hash on the blockchain. So now the contract refers to the blockchain, and the blockchain refers to the contract. That's called an asset ID, but it doesn't really matter. So what does that look like? When you're issuing this thing, you still see an op-return output, and that op-return output that you're seeing here is the hash of the contract. And then when you're spending it, you have this application. I think I ignored that part. Let me go back a little bit. So when you issue it, you use a program called Kaleidoscope in this case, and that creates the asset and broadcasts the transaction. And then when you move the asset, you use this other super tiny command, but it basically says Kaleidoscope send to address, and then you enter a normal Bitcoin address that somebody else gave you, and then you enter the asset ID and how much you want to send. So I'm sending 100 Finny towards somebody else. This creates a bunch of transactions on the blockchain, which includes a transaction to that address of real Bitcoin, but the Bitcoin amount that you're moving is just symbolic. It's just sort of a decoy. But there's also, again, this little op return in the third output, or the second output, that basically describes this transaction. Then what you do is your software is uploading, because the transaction doesn't really mean anything, so how do you then interpret it? Okay, so you create a proof, it's basically a file that gives all the extra information that the other side will need to interpret it. And you upload this proof to a server. And that could be any server, it could be your own server, it could be some random server. You could email it. Don't worry too much about the server. It's just a file. In my demo, I've actually created a zip file that you can download. And then the software on the other side is going to, its wallet is going to see a transaction come in because it's a regular Bitcoin transaction, and it's going to ask the server, hey, this Bitcoin transaction, do you have any information about that? And then the server says, yep, here you go, and it downloads this proof, and then it evaluates the proof using whatever rules you want to enforce. So in this case, it's saying, okay, I need you to check whether this transaction actually belongs to this proof, and I want you to look at all the previous transactions because I want to make sure that this 100 units wasn't double spent anywhere. So it just kind of loops through. But you can make this as complicated as you want. You're doing the checking in separate software. The problem with this, though, is we're still sort of polluting the blockchain with these op return statements, which are taking up space, but also they're just revealing that you're up to something, which you don't want necessarily if you care about privacy. And so this is where this pay-to-contract mechanism comes in, and I'm linking to a blog article that is a lot better at explaining this than I am. But the idea is that you tweak the destination address to include a hash, because a public key is, or a private key is essentially just a number, and a hash of a piece of information is also just a number. So you just add the hash to the private key, and then you create a new public key, which looks like any other Bitcoin address. This is also used in a Bitcoin enhancement called Taproot, or a similar mechanism. And if you ask Aaron van Weerdem, the well-known Bitcoin magazine journalist, he wrote a good explainer about that recently. But just to give you an idea, these kind of techniques are used for very different things. So there's a lot of smart people also making them better, which is good. Again, one of the pictures that describes this in the documentation, which I don't necessarily find super convincing. So this document will be on my GitHub. So my name is Sjors. So if you go to github.com/Sjors, you will find the instructions. But now the question is, how do we scale this? And there's two ways. Because the problem here is you're still making one Bitcoin transaction every time you're changing something in your smart contract. So your smart contract could be as complicated as you want to, but it's always one Bitcoin transaction. That's good. That's some form of scalability. You don't have to make like a 100 megabyte smart contract. It's just a hash. But maybe you have a system that's moving, thousands of things every second, and you don't want to do that, obviously, by making individual Bitcoin transactions. Key there is to combine multiple state changes and then occasionally broadcast them. And one way you can combine that is with this magical thing called the Merkle tree. You basically compress, say, a day worth of changes or an hour worth of changes. It just depends on how often you really need to commit it. And the magic for that, apparently, is called Proofmarshals. And that's the guy on the right, Peter Todd, who's going to make an implementation of that, but he hasn't done it yet. So when? I don't know. But that could be your homework, or at least I think you should read up on that or maybe ask him some questions. But the idea is then somehow to make a proof like what I just described, but not about one change, but about a whole set of changes, and ideally such that if you want to verify the proof, you don't need to study all the changes. You only take the parts of the Merkle tree that you care about. The other solution to scale this thing is using Lightning, using something called collared channels. And the idea, and that doesn't work for all types of smart contracts, but if you have a fungible contract, so something like a token, like what I just described, you care about getting 10 finis but you don't care about which 10 finis. You can't do the same with CryptoKitties. When you have a CryptoKitty, you care about your specific CryptoKitty. You don't want some other CryptoKitty. But if you have that, then it turns out that you can actually reuse a lot of the technology that's used by Lightning and just add like one little flag saying, okay, my Lightning channel is about this token. And if you don't understand that, dear other participant in the network, just ignore me. Because in Lightning, when you're a node, you can signal what your capabilities are. And you can and then there's a rule that certain types of signals, if you don't understand them, you can ignore them. And there's other types of signals that if you don't understand them, you have to abort because you might break something. And so then you indicate that you can understand this special type of red token, or a red token is the example here, but in my example, this stablecoin token. And then you can create Lightning channels just like any other Lightning channels, but it happens to have this special token in it, which is pretty cool because it means you can leverage all the infrastructure that's already there with just a few changes, rather than trying to build your own chain from scratch. Okay, so this really brings me to the homework slide. I think I'll have some time for questions even. Your homework is study this particular protocol that I just talked about, RGB. Then your homework is to actually improve it, or not. And then if you don't like it, well, this is an open source world, so don't expect other people to fix things for you. You can do it yourself. So one way you can help out, what I've done is when I was making these slides and I was trying everything out myself, I got confused a few times. So I just created a bunch of issues on their GitHub repo saying, hey, this is not clear, or I think this will crash, or et cetera, et cetera. And I even added a README file to one of their projects. And that's kind of how open source works. You try to use something for your own purpose, you find problems, you help out fixing those specific problems, and if enough people do that, the thing gets really good. And so the instructions for the Ethereum giveaway are on my GitHub account. And if you into PGP, please sign my key. That's all.